Good morning. How's everybody doing today? Happy Monday. And of course, happy last week. Kind of crazy. Winter quarter flew by. Uh, I think I say that every quarter, but yeah, the quarters get faster to me. So yeah, we've made it. We're here. So we do have one last topic to cover. So that's acids and bases. But if you check things out, I did open up the exam week already. And, I know many of you are on different schedules or traveling and have plans. So I wanted to give everybody as much time as possible to have that exam folder open. There's also a practice quiz in there. So you can, take that a few times, get a little flavor of the exam and feel really good about it. And then, of course, the exam is both there's a exam part, and so that's kind of like before the multiple choice, little bit of free response, short answer, and then the lab practicum. I'll put that, so both exam and final lab practicum as before. And of course, if you have issues, just email me and we can fix those. And of course, ask questions in the chat, or if you have anything, questions about the end of the quarter, just let me know. And I apologize in advance. Spring is here, so I hope everybody survived the time change okay. And yeah, everything is in bloom. My allergies, though, are out of control, so I apologize in advance. All right, let's dive into our chapter. So our last chapter, like I mentioned, is acids and bases. And so let's just discuss properties of acids. And again, you can chime in with your experience because I'm sure you all have interacted with acids, whether you realize it or not. And so acids have a sour taste. And so start thinking of acids you may have eaten. Lemons, vinegar is an acid, so something with a sour taste. And so many of these dissolve metals. We've seen that in a couple of our videos with like our hydrochloric acid and magnesium. And of course, they neutralize bases. And then if we had litmus paper, it would change our blue litmus paper to red. And so here are a few examples of some common acids and their uses. So we have hydrochloric acid. So this could be used for metal cleaning or food preparation, different ore refining, so like metal refinery. And it is your component of your stomach acid. And so your stomach has a pretty low pH, and well, that's why. And then we have sulfuric acid. So that is found in batteries, could also be used for fertilizer or explosive manufacturing, used for electroplating copper. So that would be important in like metal fabrication or metallurgy. We have nitric acid. So nitric acid is used to make fertilizers or explosives, and then it also dyes. Acetic acid. So this is the chemical name for vinegar. And so vinegar is just a dilute version of acetic acid. Then otherwise can be used in manufacturing. And there again, food preservation as vinegar. So next is citric acid. And so obviously this is what gives lemons and limes its taste. But if you isolate citric acid, it's like this powder thing. And so citric acid is used in a bunch of like candies. And some of my favorite are these Zots. And I had actually never heard about them till recently. And so there's this little candy that fizzes. And so all it is citric acid and then sodium bicarbonate, so baking soda, basically. And if you eat one of these candies, you notice you get this like fizzy reaction in your mouth. They're pretty fun. But yeah, citric acid is used in a lot of candy production was where I was going with that as well. So anything that's sour is usually citric acid. So like the warhead coating is probably citric acid powder. I just had some like really great Laffy Taffy warhead things, and they were citric acid on them. All right, then we have carbonic acid. And so carbonic acid goes through, so it forms this equilibrium from dissolving carbon dioxide. And so then we get carbonic acid. And so that's going to be present in any of your carbonated beverages. I don't have my carbonated water today, but obviously it could be in sparkling water or soda. And then we could also talk about the equilibrium. So there's equilibrium of carbonic acid in our ocean as well with dissolved CO2. But everything is one big equilibrium. And then hydrofluoric acid. So that is used for metal cleaning and glass frosting and etching and chip manufacturing. And then last is phosphoric acid. So that's used in fertilizer and then also is a component of biological buffers. And then you have some phosphoric acid in sodas usually. So soda will have a bit of phosphoric and carbonic acid. And so let's take a look at these, what are called organic acids. And so it says that they have this carboxylic acid group and it has a COOH, but let's draw that out. And it is actually drawn out over there, but I like drawing it. So it means we have a C and one is double bonded to our oxygen. And then this is the what I would call the acidic proton. So it can come off That makes it acidic. And I'll write this. So minus H or plus H, depending what direction you're going in. So we can pop that proton off, and then we can see how it's stable. So then we're left with this. So our carboxylate ion. So now it's charged, right? Popped off the proton. But then why this is so stable, so why this is an acid, and what we need to recognize is that it is resonance stabilized. And so all that means is we can draw this like that. So move those electrons around. And now our negative charge is shifted over to this oxygen like that. And so now we have resonance. So we're saying, right, this negative charge is distributed over these two oxygens. So that makes it really stable. So that's why it's favorable for this carboxylic acid group to lose this proton. So that's why we say it's acidic. And so there it is. Yes, this proton is acidic. And so that was the explanation as to why. And so any organic acid is going to have this structure. So I should have put a little R there to show that it is grouped to something else. So it doesn't matter what this R is. And so there are some versions. So citric acid, of course, and then malic acid, like in grapes. So just other variations of acids there. All right, shifting to bases. And again, feel free to put any thoughts in the chat or anything, even just like, oh yeah, this is my favorite acid or whatever. And so now we have bases. And I don't know if people still do this, but back in the day, right, people used to get their mouth washed out with soap. And so maybe you would have tasted some soap. And well, why that's not a good experience is because these bases taste bitter and so very alkaline. And so usually something that's alkaline is poisonous. So that's why, obviously it's not something that we want to ingest. And I don't encourage you to try to eat bases, obviously, unless it's like, milk of magnesia, something meant to be eaten. And so they feel slippery to the touch. And you also kind of get that with soap, or if you touched a little bit of bleach. Again, I don't encourage that. Don't want to hurt yourselves. And then, of course, bases neutralize acids. And then they would change red litmus paper to blue. And so here are some common bases. So again, sodium hydroxide. So sodium and potassium hydroxide are both used to make soap. So it kind of depends on just the recipe. Both they're used interchangeably. And so then and so that's also what is called sodium ash, so they used to get that from like burning wood. So like literally ash. And so then they can also be used for plastic manufacturing. You can also see cotton processing, also using like water. So this was actually something that happened recently to our Medford water here, if you happen to be local. And so they are changing the pH slightly of the water to try to prevent metal ions from coming off. So of course, metal, like we mentioned. So now this is real life application. So we said, right, something that is more acidic tends to have that ability to dissolve metals. And so they're making a small adjustment to the pH in our water. So they're making it a little bit more basic. So again, this is all on a very small scale of how much metal you're losing. But over time, right, we don't want those metals leaching in. And so they're changing the pH with a little bit of sodium hydroxide. So that's also what it can be used for, is pH adjustment in our water treatment plants. And so if they don't use sodium hydroxide to adjust the pH, sometimes they might use sodium bicarbonate, so our baking soda. And so this is often used as well to adjust the pH, maybe make alkaline water or give it kind of a flavoring. So that's also what you find is, like why people like Dasani is they just have different ions in them or taste. So different like magnesium carbonates and things like that. So that's why you like certain waters. And then sodium carbonate. So this is used as a glass and soap manufacturing again, but also just water softener and cleaner. Then ammonia is an important base. So this is used as both a detergent, but also fertilizer. So this is, I like that. The big use for ammonia is fertilizer, but also can be used in explosives and also other uses as well. All right, let's look at this hydronium ion. And so there's a couple of things that it's saying. And so what it's saying is, so really you're not going to ever have what I would call, right, this naked proton here. And well, actually, I'm going to go through what happens. And this comes a little later in this chapter, but it's good to discuss it right now. And it's that water can auto ionize. And so what that means is we have water staring at each other like this. But then what if one of them comes along and we have our oxygen here with our electrons, and so it can go ahead and pick up this proton. And so if it picks up this proton, those electrons go back to our oxygen. And then we're left with our dissociated water. So now we have hydroxide plus hydronium. Oops, sorry. Shouldn't have drawn it like that. Put my plus sign on our oxygen. And so this happens. But we're also saying, well, anytime that we have an acid, so let me label this. So water autoionization. So earlier, let's go back to our carboxylic acid, for instance. So let's say, well, we have an organic acid. What's going to happen is this proton is not going to just fly off. So that's kind of what this is getting at, is we're not just going to have this proton flying off. The action needs to be initiated by electrons. And this is really key because sometimes you go look at other chemistry resources and it might have, like proton attacking. And that is super wrong. So if you ever see that, that is wrong. So action should always come from our electrons. So now in this case, water can come along, act as our base. And we're going to learn that water can be both an acid and a base. And so now it's acting as our base, donating electrons. So now it's going to pop off this hydrogen. And so now we're going to get that carboxylate ion like we saw earlier. And then, of course, hydronium. Because again, we don't just have a lone hydrogen. Oh, sorry, I went crazy with those charges. We have hydronium. Now, that being said, chemists just use the two terms interchangeably. So usually we just write H plus. And we don't distinguish. So just know that that's used interchangeably. But in reality, right, you have hydronium. You don't have just H plus floating around in solution. Questions about that? And so now this starts getting us into the definitions of what is an acid, what is a base. So we kind of talked about some properties, but now we'll go through some of these definitions. And so let's start with the Arrhenius definition. And so let's scroll down. So our Arrhenius theory says that acids produce H plus ions in solution. Again, we know that there's not actually H plus ions, but rather hydronium. But for our purposes, we're going to abbreviate. And so we're looking at a strong acid here. So this would fully disassociate into H plus ions, or again, hydronium and chloride. So we make a bunch of H plus ions. So we know this is an acid. And then something like a base, like sodium hydroxide, we can add in there, right? Calcium hydroxide, magnesium hydroxide, just go crazy. But anything that produces OH ions is a base. All right, so that's pretty simple. And then we can look at these acid-base neutralization reactions. And so don't forget that these are really double displacement. That's all it is. And then it's driven by the formation of water. So there's our neutralization. So water drives it forward. And of course, they swap partners like we would in a double displacement. And so we make water. So our H plus ions go with our hydroxide, make our water, and then of course we form our salt. And our salt would still be ions in solution, right? So we have our aqueous term here that reminds us of that. Because I want to emphasize that it's the water formation is what drives us forward, right? Not the salt. And so the problem with this is that it's too narrow of a definition. So it doesn't explain why ammonia forms a basic solution, even though there's no hydroxide ions. And it doesn't explain how sodium carbonate is a base or sodium oxide is a base, even though they don't have hydroxide ions. And so it also doesn't explain how CO2 dissolves and makes acidic solutions. And so the problem with Arrhenius is it's just too narrow. And so now we go to this Bronsted-Lowry definition. And so now it defines what happens. So now any reaction that transfers a proton from one molecule to the other is an acid-base reaction. And then it doesn't matter whether hydroxide ions are present. And so now the definition is changed a little bit. So our acid is defined as our proton donor, and our base is now defined as a proton acceptor. So we're going to see that. And so now we bring into these terms conjugate base and conjugate acid. So let's kind of walk through this. So we start off with our acid, and let's look at a Bronsted-Lowry. Let's look at ammonia and water. So we have water. So water, as you'll see, is acting as our acid. Then we said ammonia was a base. Now let's figure out why. And so what happens, let me redraw water. That's not helpful. So let's draw it like this. And so now in this case, nitrogen has some lone pairs. So it's going to go ahead and attack this proton because remember, action has to come from the electrons. And so now we make ammonium. And so now this is explaining, okay, well, this is what happens, right? We see our base. Our base is our proton acceptor. So now we make HB. And so now that it has more protons, this is called our conjugate acid. So our conjugate acid was our base. Now it has protons. Now it's in its conjugate acid form. And then this leaves water with less of a proton. And so that leaves it as hydroxide. So now we see how we can form hydroxide ions, even though ammonia didn't have any. And then we are left with what we call our conjugate base. And so we can look at this definition, how it applies to water and hydrochloric acid. So hydrochloric acid is our acid. It disassociates to make chloride, which is our conjugate base. And then that goes on and reacts to make our acid, so our hydronium or H plus. That's our conjugate acid. So there's our scenario with ammonia. So again, we walk through that. Ammonia can accept that hydrogen, make ammonium, become our conjugate acid, and leave hydroxide as our conjugate base. And so what's kind of nice about this is that we can really see the equilibrium, and we'll get into that as we talk more about our weak acids. And so if you kind of remember, we talked a little bit about this with the light bulb. And so we mentioned that our weak acids do not fully disassociate, unlike our strong acids. So they'll be in some sort of equilibrium with its acid form and then making its conjugate base. And so you want to be able to identify conjugate acid base pairs. And so the key is that there always one proton difference between them. And so sometimes you'll see like, oh, pick out these conjugate base pairs. And then you'll see this. But is this a proper conjugate base pair? What's the issue? So if we look at this, the problem is that they're two protons difference. So they would not be a good conjugate acid base pair. That would mean hydroxide and water. That would be our base and conjugate acid pair. And then, right, water and hydronium. So this would be our base. This would be our conjugate acid pair. And so that these all have one proton difference. All right, try this example out. See if you can figure out who's the acid, who's our base, and then who's the conjugate acid, who's our conjugate base. let's start walking through them. So I'm seeing, so we have sulfuric acid. So I'm thinking this is probably our acid, but let's just kind of double check what happens. So then we have water. And then, oh, okay, this gets deprotonated. So this looks good. Okay, I'm going to call this my acid. Then this is our conjugate base, right? Because now it lost one proton compared to our acid. And so that means water is acting as our base then. And yes, it formed hydronium. That makes sense. So now this would be the conjugate acid compared to our base of water. So now we have this hydrogen carbonate species plus water. And so now it looks like it's gaining a proton to become carbonic acid. So now I'm going to say this is our conjugate acid since it has one more proton than what is our base. And now water is an acid. And we are left with hydroxide. And compared to water, right, one less proton, so that is our conjugate base. Questions? Let's go back to the last definition because we don't really talk about it, but I didn't want to just skip over it. And so the last one that kind of goes beyond is based on electron donors and acceptors. And you've kind of seen how I've done that, our electron action. And let's bring up a Lewis acid base pair just so you can see what that means. And so the classic example of a Lewis acid base pair is going to be like ammonia. Of course, let me draw it out. And then a borane. And so I'll just pick BF3 for simplicity. And so in this case, boron is acting as a Lewis acid. And so we see that it's an acid since it's a substance that needs or will accept an electron pair. So in this case, why I brought up borons is boron tends to be electron deficient. So it has 3 valence electrons. So it tends to make these compounds, right, with 3 other substituents, but it only has 6 total electrons. And so because of this, borons are all thought of as Lewis acidic compounds. And so we see that this nitrogen will go ahead and donate. And so notice this is a funny type of bond. And so nitrogen is contributing both electrons in this bond. And sometimes you might see a paper draw a bond like this. And so this is called a dative bond. But basically it means whatever direction the arrow is showing. So we're seeing that nitrogen is donating 2 electrons to boron. And so this is also not a normal bond. So this is heterolytic. So it's split heterolytically. So all those fun terms. But this gets, so this is again the most expansive definition. So probably won't discuss this too much more in this class, but you should still be aware of it. And this is, also like how you work to make batteries and other things. So that's where you want to think about this. And a lot of research in chemistry is on these what are called frustrated Lewis pairs. And all that means is that they're Lewis pairs like that, but maybe you hold the compounds in some geometric ways so that they can't really get to each other. And so that means that they're going to do cool stuff, at least hopefully. That's always what you hope. And so now here's where we get into the strong versus weak acid and base. So again, we kind of touched on it with our disassociation. So going back to non-electrolytes versus electrolytes. So we said non-electrolytes were our molecules and they did not disassociate. And then we had ionic compounds, which did disassociate. But now we have acids and bases. And so some of them have an equilibrium. And so again, we mentioned that a strong acid just undergoes complete ionization, right? It has nothing to do with how dangerous it is. Hydrochloric, nitric, those are just two examples of a strong acid. And then a weak acid is going to be something like HF or vinegar, or phenol is a weak acid. So now these are organic compounds, but those are weak because they are partially ionized. And so that means they have some sort of equilibrium, which we will see with this equilibrium symbol. Same thing applies to our bases. And so most of our bases are strong electrolytes. So again, that's all our hydroxide, all our ionic compounds. So I'll just put ionic hydroxide compounds. But then we will have a few weak bases. And so most of them, though, are going to be ammonium or ammonium based. So that's ammonium. I could also write methylamine. So this would be a weak base. And so again, with these, only a small percentage is ionized. And let me make this clear, right? There's no methyl hanging off of it. That's just regular ammonia. This would. So still is our lone pair. And so now these are just kind of general trends. And so the stronger an acid is at donating a proton, the weaker the conjugate base is at accepting a proton. This is kind of weird. I think we'll go back to this. It's a good saying though, but I don't want to dive into it right now and dissect it. Other trends are higher oxidation number, stronger the acid. So you can see that compared sulfuric versus sulfurous, nitric versus nitrous. And I'm sure there are uses for these, but honestly, I've only ever worked as sulfuric and nitric, so never the lower oxygens. And then cations are stronger acids than neutral molecules. And so we generally see this that anything that has a cation tends to be an acid. Neutral molecules are stronger acids than ions, and then bases or anions are the worst acids or the best bases. So trend in base strength opposite. Here's maybe where we can start to dissect that statement a little bit. And so we have these acid base pairs. If we look at this, so let's just start with HCl and what this means. So again, we said strong acid fully disassociates. Okay. And so now let's go back to this saying. The stronger an acid is at donating a proton. Okay, so we had our base, we have our acid. So strong acid, hydrochloric acid. So, right, donated that proton. But then it says the weaker the conjugate base is at accepting a proton. And what this is saying, so this is such a good acid, right? So this is HA acid, that its conjugate base, so the better it is at donating proton, the worse its conjugate base is at accepting it. And so what would that reaction be? That's literally describing that reverse equilibrium we were talking about. So we're saying that chloride could it, right, donate electrons and pick up the hydrogen. But if we go back to the saying, the weaker the conjugate base is at accepting a proton. So this conjugate base cannot do that. That is what we are now saying, is that this will not happen because our equilibrium lies all the way to the right. So chloride is not going to ever form HF. So that also means, right, you can put sodium chloride in solution, right, and then it's not going to form HCl. So that's not the case with other salts. And so that's why these bases here say, right, do not undergo base ionization in water. So they're just ions in solution. So they do not reform their acid. So that's our key. Let's skip down, though, to HF. And it doesn't have that. And so HF is a weak acid, which is, it always kind of freaks me out because HF is kind of scary. And it's only scary because if you get it on you, they say you may not really notice, but then it'll leach down and go to your bones and it might dissolve the calcium in your bones, and then that could re-solidify somewhere else. And then if it re-solidifies, depending on which blood vessel it re-solidifies in, that could be a stroke or something bad, heart attack, don't know. All right, so HF, now it has an equilibrium. Now we have fluoride and H+. And now we're saying, yes, fluoride can reform HF. So that means we have fluoride. And now let's just react it with water to show it's going to happen. So now it's going to make HF in solution and then leave hydroxide ions as well. So then now we can say that fluoride is our base. And since this is weak, so then go back to this saying, the stronger an acid is at donating a proton. Well, now this isn't so strong, right? And so that means that, so it says the stronger, then the weaker the base. Well, if it's not that strong, then our conjugate base could accept a proton. And so this chart is super helpful just so you can kind of see, well, who are my strong acids, who are my, weak acids, and have an equilibrium. So this will kind of help you, and it helps match up your conjugate base pairs. And for example, right, you have carbonic acid, and then it loses one proton to make our hydrogen carbonate. And then our hydrogen carbonate is paired with our carbonate. So you can see how those steps work in solution. And so let's kind of look at this Ka thing. And so just in general, so we're looking at HA, right, splits off to A minus and H plus, or also hydronium. So then our Ka is going to be equal to products, right, over reactants. So the concentrations of, again, our product species, so that would be dissociated A minus times our concentration of hydronium over our original, over our HA. And so if we had a strong acid, equilibrium lies strongly to the right, favoring our products. And so we say our Ka is greater than 1, right? So again, products over reactants, just thinking more simply rather than a math expression. And so I would maybe write this down or start this again. It is shown over here 1, 2, 3, 4, 5, 6. But just as a reminder, those are our 6 strong acids that fully dissociate. Now, weak acids have a Ka that is less than 1, and so they only donate a fraction of our ion. So we only have partial ionization. And so common weak acids are acetic acid, carbonic acid, and formic acid. And so we'll look, this is a good table. And so something we notice is that as our pKa's increase, their strength decreases as an acid. And so we also have our equilibrium constant. And so we can go between the two. So our Ka, or excuse me, let me rewrite this a better way. So pKa is equal to the negative log of Ka. And so this is a good time to test your calculator. So the only issue with this chapter is you have to make sure your calculator is in the correct log. And so let's double check that. So negative log, and let's do nitrous here. 4.6 times 10 to the negative fourth. That gives us our pKa, so we can round that in. What's interesting, so for sig figs, if you have 2 sig figs that go in, you can report to 3 sig figs on your calculator. So you add an extra digit when you do the log. So now your pKa should be 3.34, which that's what they have here. All right. This is probably a good place to stop, and then we'll save the math for Wednesday. So then we'll get into all the math with it. And so start looking at how to calculate our pHs. And so, of course, reach out if you have any questions about anything. And then we'll go over all the math on Wednesday. And again, good job with this quarter. Everyone has been doing really well. So just keep it up to the end. And the exam should be open as well for your pleasure. All right. Thanks again. Have a great rest of your day.